thought these were all covered in the carboxylic acid chapter. Of course, going through it, I thought, man, there's a lot of details that are missing. So we're going to get all the details about acid derivatives. They all pretty much look like derivatives except for maybe this one, nitrile. Of course, all these can be converted back to the acid, which is missing. All of these, if we hit them with water and have some acid or base catalyst, maybe a little heat, we say hydrolysis will take it back to the carboxylic acid. Water will split off a halide, put an OH there. Water will split that apart, give us 2 carboxylic acids. Same thing with the ester, the amide, and this will turn into a carboxylic acid. Amides, think of proteins, so they're everywhere in nature. Esters, a lot of flavorful things made in nature from esters. So how do we name an ester? Well, look in here. The green is the IUPAC, and we name them as a alky carboxylate. So remember when we named the acid salts, let me just bring one up here. Our favorite, acetic acid. Let me just name it. Well, that's not how I do it, but I get to ethane, then I go oic acid. All right, now if for some reason this gets deprotonated, and I have something like that, I get rid of ic acid. I always think of oatmeal, but O8. So this would be sodium ethanoate. Now if I make an ester, now I'd name the alky group. Maybe I should make a methyl group so it's not as confusing. So the only confusing part is I've written this backward. Here's the methyl part. Here's the ethonate part. Methyl ethonate. So now if we look up here, 1 carbon, methane. So here's our methonate, 1 methylene. I would opt for isopropyl methanoate. So H, benzoic acid, the anion, benzoate, the alky group, phenobenzolate, methyl, 2 carbon chain, ethanoate, phenyl on number 2 carbons. So methyl 2-phenyl ethanoate. Here's another methane, methanoic acid. So cyclohexomethanoate. First word is derived from the alky group of the alcohol. The second word from the carboxylate of the carboxylic acid. Any questions? Cyclic esters. That's something new. Reaction of an OH and the carboxylic acid on the same molecule can produce a cyclic ester, which we call lactones. So just for fun, that first slide said all of these can undergo hydrolysis. I think I checked on that one. So an OH and a carboxylic acid group on the same molecule, we could do like Fischer esterification in the other direction, in which case you wouldn't be dilute, you'd be more concentrated. So cyclic esters are also called lactones. To name, add the word lactone to the IUPAC acid name or replace the ic acid of the common name with allolactone. I'm going to stick with the IUPAC names. 1, 2, 3, 4, 5. 5-hydroxypentanoic acid, lactone. Let's do our base catalyzed hydrolysis. Oh, knew it wasn't going to be simple. Well, there's kind of a curveball with that thing. So 1, 2, 3, 4. 4-hydroxy. What? That's not right. How about 2,4-di? So, any question on how to name cyclic esters? Amides. So we saw this in the last chapter. You got to heat things up to like past 100 degrees Celsius. You drive off water. You get the amide. Why is it showing up again here now? Well, because they're a product of a carboxylic acid with ammonia or amine. So here was the interesting part I'd kind of forgotten about. Not basic because the lone pair on nitrogen is delocalized by resonance. Now I could draw water and put a proton off on there. This carbon nitrogen bond has a double bond character. Why don't I play with that for just a little bit? So here's what I want to do. If I drew that arrow, I could produce hydroxide and I would claim this as basic. But what the book is saying here is this jumps down and that jumps up. Put my water back in. Now these electrons thought they were going to grab Mr. Proton off of water and make hydroxide, but resonance takes over. Now, there's the double bond character. And this will explain one other physical property about amides, which I found to be kind of interesting. When you protonate an amide, it says a concentrated strong acid is required. Normally just weak old ammonia, you can protonate it with weak HCl, puts proton right on that lone pair on nitrogen. However, the proton doesn't go on that lone pair on nitrogen. It goes to the oxygen on carbonyl carbon, as seen here. I'll come back to haunt us in just a little bit. Classes of amides, primary, probably don't see those too often. See all these all the time in biology. I guess you see these because the side chain. Tons of these in biology. So primary, one alkyl group, secondary, two alkyl groups, tertiary because of three things bonded there. Now, how do we name amides? For a primary amide, drop ic or oic acid from the carboxylic acid and add the word amide. There's our IUPAC name for vinegar, ethanoic acid. So down here, I'm going to delineate what's on the nitrogen and ethyl, and I've chopped off the oic and added amide. I'll do the real simple thing here. Ethanamide. So I imagine the acid and get 2-methyl propanoic acid. Get rid of the oic acid and write the word amide. So now I have all this business. N-ethyl, N-methyl propanamide. So we saw this in the amine chapter. Alky groups bonded to nitrogen are named with the N-alky to indicate their attachment to the nitrogen atom. So it's just like our other substituents. If I have 2 methyl groups and the word di, I better have NN. Cyclic amides called lactams. Makes me want to back all the way up. I didn't want to do that. Lactones, I should just go over to the computer. And lactams, lactones and lactams. To name, add the word lactam to the IUPAC acid name or replace the ic acid with the common name olactam. We're not going to mess with common names. So they did what I did with the lactones. Got to break this apart to figure out how to name it. 1, 2, 3, 4. Butane, butanoic acid, nitrogen group on the number 4 carbon. 4-amino butanoic acid. Put this thing in a cyclic setup. 4-amino butanoic acid lactam. Let me see if I can handle it without this. 1, 2, 3, 4, 5, 6. 6-amino hexanoic acid lactam. So just adding the word lactam to the IUPAC acid name. Nice and straightforward. So here's some new chemistry, and I think this is very important because in other chapters, all those times you can do substitutions and make a nitrile. So all the chemistry we can do with a nitrile, we can get from some other building block, our alkyl halide, the basic building block of all organic chem reactions, or a large portion of them. We base or acid catalyze, add some water, we get a primary amide. Of course, that can keep on going to the acid. We also call this a cyano group, and we can get the carboxylic acid from that. That's why in this chapter it's called a derivative of a carboxylic acid. So let's just review our triple bond chemistry. sp hybrid carbons on an alkyne. So this is an sp hybridized carbon. This must be an sp hybridized nitrogen. But we got 2 unused p atomic orbitals in the parallel overlap constituting a pi bond and the beautiful 180-degree bond angle. Now, one interesting thing here, they tell us lone pair of electrons. So my question, is that a basic? Because I can't draw resonance structures. We just saw that the amide isn't all that basic because the double bond nitrogen carbon property. Not basic. So how can we get a nitrile group? We can start with carboxylic acid, add some ammonia, heat it up, get our primary amine, and we have these phosphorus compounds. This is phosphorus in the +5. There's a whole slew of these things, and that forms the nitrile. Dehydration. How do we name nitriles? Fairly straightforward. Add nitrile to the alkane name. 2-carbon chain, ethane, ethane nitrile. 1, 2, 3, 4, 1, 2, 2 bromobutane nitrile. Doesn't get named as an ether, does it? Well, we could pretend this was a CH3 and we would get 1, 2, 3, 4. Well, it's fairly similar. So this is 5-methoxyhexane nitrile. And we don't want to worry about common names. Acid halides. Normally that's how we like to do some of our fancy form an ester without using the Fischer esterification. And another ways to form an amide is to use an acid chloride. We'd treat the carboxylic acid with thionyl chloride, also called acyl halides, more reactive than carboxylic acid, so are they're used to synthesize other acid derivatives like our esters and amides, as we saw in the carboxylic acid chapter. Most common acyl halides are the chlorides. Acyl chlorides. How do we name these? We actually saw it in the carboxylic acid chapter, named by replacing ic acid with ly, and then the halide name. Ethane, oic acid, drop the ic acid, and then the halide. So this becomes ethanoe fluoride, propanoe chloride, 3-bromobutanoe bromide. Just play with this one for fun. How would I name that? Cyclopentane carbaldehyde. Excuse me. There we go. I was choking there for a second. So get rid of ic acid. Well, that one didn't work out so well for me. Don't know what to make of that. Acetyl chlorides are more common. So when we made aspirin in lab, we used acetic anhydride. Guess that's a common name. And I pointed out why we if we had acetic acid and went this way, we'd take water out of it. 2 molecules of acid combined with the loss of water to form the anhydride. And anhydrides are more reactive than acids, but less reactive than acid chlorides. So if you imagine this being the OH on salicylic acid, that's how we made our aspirin. In acetic, in an anhydride, the carboxylate group activates the carbonyl. Carboxylate ion is the leaving group in a nucleophilic acyl substitution reaction. How do we name anhydrides? The word acid is just replaced with anhydride, ethanoic anhydride, but this is so common we just tend to call it acetic anhydride. Phthalic anhydride, here's something that's interesting, malic anhydride. For mixed anhydride, name both acids. All right, now we're really going to mix it up. What if you have a cyanide group and an ester group, an aldehyde and an amide group, a nitrile group, and an alcohol group? Not a problem. I go to that list of priorities and see which group has the highest priority. And carboxylic acids are pretty much at the top. So I imagine, like here, since this is a carboxylic acid derivative, of course we can't tell because, well, I mean, too bad they didn't put the OH over here. Then we'd be competing. Do we number from this end or this end? So this one's fairly straightforward. 2-hydroxybutane nitrile. Aldehyde looks to me, no, this is the acid derivative, and they're naming this 2-formally cyclohexane carboxamide. Ethyl orthocyanobenzoate. There's the benzoate. I should have pulled this up at the beginning. Acid, ester, amide, nitrile, aldehyde, ketone, alcohol, amine, alkene, alkyne. Probably put a comma in right, alky halide somewhere down there. That about covers it. To summarize our nomenclature experience this morning, we have this table. We have our functional groups: carboxylic acids, esters, amides, nitriles, aldehydes, ketones, alcohol, amines, alkenes, alkynes, alkanes, ethers, and halides. And there's a typo there, Eric. In order of decreasing priority: oic acids, OHs, amides, nitriles. For whatever reason, when we name a carboxylic acid as a substituent, carboxy, cyano. This is one I've hardly ever used. Amido, amidal. Let's stick with amido. Formerly oxo, hydroxy, amino. Any questions over the nomenclature? We will adjourn early today.